2.8 is the derivative as a function. It says here derivatives are instantaneous rates of change and have widespread applications and implications. One application we've talked about already is the instantaneous velocity at a particular t equals a value. So note that this was something that we didn't have before we started talking about calculus. This is something that before we had with algebra, an average velocity. So looking at the change in distance over the change in time as an average velocity over some time interval. And so we have a philosophical leap here with calculus. It allows us to talk about instantaneous rates of change, which have a lot of applications, not just at looking at the velocity or speed of an object. As a whole, calculus is sometimes referred to as the mathematical study of change, and also we can talk about that study of change from the perspective of being very precise now with the introduction of this limit and the derivative. So from 2.7 we talked about the derivative of a function at a particular x equals a value, and so a reminder there of that definition. It turns out to talk about the derivative as a function, all we have to do is replace the a's with x's, and then we talk about the derivative function f prime of x. It turns out that this limit on the right is something that you can actually evaluate if you just leave x in there instead of a particular a equals 3 or something like that. A is a value. Then what that allows you to do is to get a little function or like a little equation for the derivative called f prime of x. And then if you want to find the instantaneous rate of change at a bunch of different particular x values, you have that formula and you just plug in that general formula after the fact. And so I've written out this definition instead of just telling you what it is. It says the derivative as a function of x is a function f prime of x describing the slope of a tangent line to f of x at any point x f of x. This is also the instantaneous rate of change of f of x as a function of x. And so we have a lot of different notation for this that I'm just trying to get you accustomed to. Mostly we're going to be using this Newton notation f prime of x. F prime is another form, or y prime, meaning the derivative. Later on we'll talk more about Leibniz notation, which is dy over dx. All those mean the limit as h goes to 0 of f of x plus h minus f of x over h. That is the definition of a derivative as a function. So before we would launch into doing a bunch of examples where we're actually figuring out that derivative function using this definition that's boxed off here, we're just going to get out of the way some of these other definitions and things. So the first one we'll talk about is definition 3. Function f is differentiable at a if f prime of a exists. It is differentiable on an open interval if it is differentiable at every number in the interval. Now this definition seems silly because it doesn't really seem like it's saying anything. You know, a function is differentiable if f prime of a exists. Well, yeah, duh. But if we think about this as the 2.7 definition, either one, I'm going to use the x goes to a one is f of x minus f of a over x minus a. Then when we look at a particular function to see if it's differentiable somewhere at x equals a, then this limit has to exist is what that means. So there's a bunch of cases that this definition is not upheld, and so we're going to talk about those right now. So first, a couple disclaimers here of what this could mean. First of all, this first star. Let's say you find an f prime of x function and you sub in a particular a value and you get something that's not defined. That's a scenario you could have where the function is not differentiable at that x equals a. So an example of that is shown here, which I probably don't even want to talk about because it's kind of off the beaten path here, but just saying, like, if you have this derivative function, you plug in x equals 0 in this case and you get something that does not exist because you get division by 0. This is a function, not a limit, so therefore the derivative doesn't exist at x equals 0. So it would not be differentiable at x equals 0. Another scenario, highlighting this next star, is f not being differentiable is when, like I was saying before, this 2.7 definition is not upheld. And so a common place where that occurs is when f of a does not exist. If you can't plug in f of a into this limit, then you can't determine what the limit is. And so that's an issue too. So now we'll go through all the cases. I'll go over why, but when it comes down to it, you just need to remember what these situations are and that they're not differentiable there. If you don't understand why, that's okay, but I'll explain that. So the first is a corner. Whenever you see a sharp corner, like in this example at x equals a, it's not differentiable at x equals a. So let's go over why. Going back to that limit as x goes to a of f of x minus f of a of x minus a is what we're going to be thinking about for all these. So note that for this scenario, as we try to find our secant lines from the left and the right, because it's a two-sided limit, and it includes f of a always, then we're going to get slopes on the left and slope on the right that are not equal to each other. And so therefore that limit does not exist at x equals a. So it's not differentiable at x equals a. Next scenario is a cusp. Cusp is where you have kind of this pointy thing going on and not just a corner. So for this particular example I showed of a cusp, what's going on here is that, again, we have to use f of a as part of our secant lines that are approaching the slope of the tangent line at x equals a. We have to do in that way by the definition of a derivative. So on the left we get limits going of that secant line. Its slope is going to negative infinity, and from the right hand side it's going to positive infinity. Both of those don't exist and they don't agree. So there's a couple of reasons why that limit x goes to a of f of x minus f of a over x minus a does not exist, so therefore it's not differentiable at x equals a. Next one, vertical tangent line. What we have going on here at x equals a is the slope of the secant line for this one is going to negative infinity from both sides, which is not defined, or is not a value that is needed for that limit to exist. So therefore it's not differentiable at x equals a. You could have it going to positive infinity too if it was drawn with a different example. And similarly, with a vertical tangent line, you would get that that limit does not exist at x equals a. The last case is discontinuities, and we have a couple different cases of discontinuities. So for the first one, here's a jump discontinuity, and f of a does exist, it's right there. And you have to include that, however, in figuring out the slope of the secant lines from the left and the right. And so from the right you get one value, from the left you are always including that f of a, so that value is going to something else for the slope. So these two purple lines, the tangent lines, or excuse me, the secant lines from the left and the right are not going to agree as x goes to a. This next scenario, we have a removable discontinuity. F of a exists, but notice that when we include f of a, when we determine the slope of the secant lines from the left and the right, they're not going to agree. And they approach some infinity thing, which is really weird. So that limit will not exist as x goes to a. Finally, we have this scenario here where we don't even have a dot at f of a. So we just, don't have a undefined point at f of a, or a f of a. It just doesn't exist. If you can't put an f of a into the formula for the derivative, then you can't take that limit. So f of a is just flat out not defined, then it's not differentiable at that particular x equals a. Alright, so again, those are the reasons why, but really you just have to remember it at any discontinuity, or a vertical tangent line, or cusp or corner, the function's not differentiable. Finally, endpoints is something we could talk about, but in this book we don't define left and right differentiable like we did for left and right continuity. So we could talk about that, but we don't in this book. So that's why we're not going to talk about endpoints.